Hey everybody, this is Professor Walsh going over experiment 9 and the pre-lab for what to expect in this. So just so you can see, I am on Professor Sherlock's webpage, and I went down to experiment 9, and when I did, it opened up this document right here. Now, there are some objectives for this lab that are not the actual purpose. The purpose of this lab is to synthesize pure cyclohexanone. Now these objectives here are just all the learning objectives, okay? So just keep that in mind when you're writing up your general procedure. Okay, now this is an oxidation reaction that we're going to, in which we're going to use bleach to oxidize an alcohol to form the ketone. Now, just real quick, keep this calculation, or converting that to moles, to put that into the the data table, the table of physical constants. That calculation is tricky, and every year it seems like people kind of miss that. So just keep that in mind as you're doing that. Okay, so 155 milliliters, then you can use molarity, moles per liter, right, and go from there. Okay, so let's go through some of the procedure here so that you know what the heck is going on. Okay, now what you're going to do is you're going to add the cyclohexanol to this glacial acetic acid. Glacial acetic acid is just another fancy traditional way of saying concentrated acetic acid, and that stuff is really dangerous. You just want to be careful of that when you're doing that. Okay, and then you're also going to make sure that this reaction is temperature controlled. Now you're probably not going to have to heat it because the reaction itself is exothermic, but you want to make sure that as you add the bleach to the reaction, that the reaction stays between 40 and 50 degrees. If it stays below that, you may not get enough heat energy to allow the oxidation to occur, and if it goes above that, you may have too much energy and you may get more side products. So the optimum range is to keep it between 40 and 50 degrees. So as you're adding the bleach, make sure you try to keep that that temperature monitored and in between there. Now, if it drops below 40 degrees for a minute or two, is it going to be the end of the world? No. If it goes above 50 for a little bit, is that going to be the end of the world? No. Just try to do your best. Now, if it gets really hot really quick, then that's when you can use the ice bath to keep the temperature, to get the temperature cooled. You don't want to get it too terribly hot. But you're going to use a dropping funnel, okay? And so what I did is I pulled up a picture of what a dropping funnel looks like. And so a dropping funnel looks like a separatory funnel, but what happens is it has this little ground glass joint on it. What that does is allows you to have a tight seal between the two pieces of glassware, so that as it's dropping, you're keeping the natural atmosphere out of there. So it's something good to do. Now, another note that you may or may not know is you have to worry about what I call the water cooler effect. When you're using these dropping funnels, you have to make sure that the cap is off when you are trying to add the stuff, in this case the bleach, because if it doesn't, you won't get any air to replace the liquid that's dropping in, and it'll start bubbling and glubbling like a water cooler. So if the bleach isn't going in there quickly, just double check that the lid is off of the addition funnel. Also, with that, you'll probably notice that in our lab, there may not be big enough dropping funnels to fit all 155 milliliters of the bleach in, which is fine. Get your 155 milliliters of bleach, add 100 milliliters to the smaller sep funnel or to the smaller dropping funnel, and then as that goes down, again, the ground glass joint, the ground glass stopper is going to be off of that joint. You can add the bleach as you add it to. You can add the bleach to the funnel as it's dropping into the reaction mixture. It's no big deal. It's not going to affect the outcome of the reaction. Okay, so. So swirl, let it all go, and let the reaction sit for about 20 minutes. That's to make sure that the reaction goes to completion. At that point, the reaction is going to do what it does. You don't necessarily have to maintain the 40 to 50 degree temperature. The reaction is probably going to stay fairly warm. It's going to cool off a little. It's probably not going to get back down to room temperature, but it'll stay pretty warm. So now that reaction is going to happen pretty quick. And I always say that a lot of reactions in organic chemistry don't take very long. This is no exception. The actual reaction is only going to take about 30 minutes. The rest of the time in lab is going to be spent purifying your compound. And so now that you've done your oxidation, you're going to have to try to remove the bleach, any of the salts that are left over, any of the starting material that's left over. And we do that through what we call the workup. So the workup for the reaction has to start by neutralizing the leftover bleach. If we start doing workup with bleach, things could get ugly. It may not, but it could. So we're going to try to neutralize the leftover bleach, and that's what this paragraph is talking about. Check to see if there's bleach, and instead of using drops of potassium iodide, what we have are potassium iodide strips. If there's still bleach present, you're going to see the blue-black color. If there is still bleach, which is hypochlorite, you're going to want to neutralize that bleach by adding bisulfite. That compound is going to be oxidized by the bleach. It's going to then use up all the bleach. So there's a solution of sodium bisulfite. So you're going to keep adding 1 milliliter portions until that gets neutralized. I will say that in general, that's not a ton of sodium bisulfite. And sodium bisulfite kind of smells not pleasant. It's not horrible, but it definitely has an odor to it. But if you get up to 30 or 40 milliliters of sodium bisulfite for this reaction, you've probably gone too far. Something may not be right. So just be careful there. Okay. Now, because we're doing this over 2 weeks, I think the thing to try to get to is through this steam distillation here. Okay, so you're going to once you neutralize the bleach, now you're going to try to separate out the organic from the water by doing a steam distillation. Okay, so you're going to add a whole bunch of water to this. Okay. Into a 500 milliliter round bottom flask. You're going to set up a simple distillation apparatus, okay, just like we did in first semester of organic. Typically, there's one in the front of the lab during the first few weeks of lab. You can see what a simple distillation apparatus looks like, and then what you're going to do is you're going to distill it until this stuff happens, okay? And I just want to say that until the distillate, let me make sure that I have that, until the distillate is clear, remaining pot is clear, that typically is a hard thing to do, okay? So remember, there's two parts to a distillation. There's the pot, that's that 500 milliliter round bottom that you're starting with, and then there's the receiver, where it's going. Okay, so this direct steam until the distillate in the condenser is a single phase, and the liquid remaining in the pot is clear. The idea here, I think, in a practical sense, is that it's going to be tough to see if the single phase is actually in the condenser, if there's a single phase going through there. I mean, it's just drops going through the condenser. So that's going to be tough to see. And as it comes over and is in the receiver, that's going to be tough to see. So in general, my guideline is, instead of using those physical clues, there's kind of a different thing to think about, okay? Yeah, the product, the cyclohexanone that we've made now up here, is going to be mixed with the water and all that stuff, okay? And so as we distill it, we're going to distill some cyclohexanone and some water, and it's probably going to be all mixed up. It's all probably going to be one layer. It may or may not be, but that's the idea. But how much cyclohexanol did we start with? Look back at your sheet. How much? How much is on your physical constant sheet? Is it 10 milliliters, 20 milliliters? Okay, question mark. Not giving you that answer. Okay, well, in general, if we're starting with 10 or 20 milliliters or 50 milliliters of starting material, in this case cyclohexanol, how much cyclohexanone do you think we're going to be making? Are we going to be making 300 milliliters of cyclohexanone? No. We're going to make, if we started with 10 cyclohexanol, we're probably going to be making around 10 cyclohexanone. If we start with 20 milliliters of cyclohexanol, we're probably going to have about 20 milliliters of cyclohexanone. Okay, so that gives you an idea of how much product you have right from the very beginning, kind of using your chemical sense. So if you do your distillation for half an hour and you only have like 5 drops in the bottom of your receiving flask, you probably haven't gone far enough because you have nowhere near 20 milliliters. So when you're doing a steam distillation, it's always pretty good to go well beyond where you're supposed to go. So if you're supposed to get 20, 30 milliliters of product, and again, I'm purposely not telling you exactly how much product you're going to be getting. But, if you're supposed to be getting 20 to 30 milliliters of product or whatever, it's probably good to collect 100 milliliters of water to make sure that you get the last little bits of all the cyclohexanone or the product out of the steam distillation. It's better to go too far than not far enough. It's already mixed with water, right? So what you're doing is you're trying to eliminate some of the water, so that you're not doing all sorts of crazy stuff. What stays in the water as you distill? Like the bisulfite and any of the sodium salts from the reaction mixture. So in the receiving flask, you're going to have water still, but you're not going to have any of those sodium salts from the sodium hypochlorite, the bleach, or from the bisulfite. So all that's going to stay in the distilling flask. So the question I get time and time again is, am I done? Well, not being rude, but the teachable moment is, I want you to try to figure it out. So I'm probably not going to tell you. What I'm probably going to do is say, well, let's look at it. Let's come up with some observations. What do you see? Do you feel good about this? Okay. And so, because part of my job is a lab instructor, is to get you to be able to feel some of the organic chemistry more than just kind of doing it robotically. And that's part of the observations that you need to take and write in your experimental procedure. Okay, so the hope is that at this point you can take this and then you can get to this point right here on the first night. Okay. Now, if you only get to this point where you just have the aqueous layer in the pot, and then you're done, that's fine. Sorry, not the pot, the receiver, that's fine. But it would be great if you could saturate it with sodium chloride solution. Okay. Sorry, sodium chloride, not the solution in this case. And then separate the cyclohexanone and extract it with ether. So what's going on here? Okay, that's the deal. Okay, that's the next question. Okay, so what you are trying to do again, now you have in that receiving flask, you have your product, you have water, and you have maybe some starting material. You're trying to get rid of as much water as possible. So what you're going to be doing here is adding the sodium chloride. Now that's going to do two things, but primarily what it's going to do is it's going to make the water layer have more ionic character, which means that the water layer is going to separate more readily with the organic layer. Okay. It's also going to allow, maybe if there's any stray salts that worked its way over in there, it's going to keep those dissolved in there. But that forces any of the organics to form a second layer. So this is where you're going to really see two layers form. The other thing, okay, and so I'm bringing up my little drawing pad. So you're going to have a round bottom flask, and in that round bottom flask, before you add the salt, it's just going to kind of be probably, again, every lab is slightly different, but it's probably going to be, one layer. And then you're going to add salt till it's saturated. Okay, how do you know if it's saturated? Well, eventually you're going to see little salt granules down here. That's how you know it's saturated. And when that happens, you're increasing. What we're doing is what we call increasing the ionic character of the water, allowing for the separation of this will be the organic layer, and this will be the water layer. Okay, and then we're going to continue to promote that separation in the next step by then adding ether. We're going to add ether in here, and ether is an organic solvent, and so that organic compound, I'll change colors here, okay, that organic compound is now going to dissolve, and any of it that's in here is definite. So because this is now even more organic, and this is so ionic, oil and water don't mix, you're going to have as much organic in here as you can. Okay, and now because this is two really easy layers to see, now we're going to take this thing, and then we're going to separate it. And you always use a sep funnel, a separatory funnel, which is this thing without the ground glass joint. This is a separatory funnel, okay, to separate layers in a liquid. Okay, so what ends up happening in the sep funnel, okay, here I'm going to try to draw a sep funnel, and my sep funnels are really bad, but okay, what happens in a sep funnel is the water layer, which I'll keep consistent, is the blue, and the organic layer, which is red. As this drains down, what it does is it just allows you to be able to see the interface well, so you can drain all the water out. Now, if you are a really, really good chemist, okay, a good technique or a good habit to get into is to take the water layer, because there's two holes in this thing. The water layer is going to drain out the bottom, or whatever the bottom is. In this case, 90% of the time it's water, but the water layer is going to go out the bottom, and then the organic layer, once the water layer is gone, should kind of be poured out the top. That prevents any junk that is built up in the stopcock or in the neck of this thing to not intermingle with the organic layer. Okay, it's just kind of a lab technique. Yeah, it's a little overkill, but it's definitely good lab technique. So now what you have is you have a container, okay, that came from, you have a container that has the water layer in it, and then you have a container that has the organic layer in it. And now you've separated the water, the junk, from the organic. Okay? Again, good lab technique, make sure you keep these labeled. Okay? You don't want to be the person that throws away what they thought is the water layer and then it actually being the organic layer, and then it's like, oh, I don't know what to do. So keep that in mind. The other thing, again, good lab technique is I try not to get rid of layers until the end of the lab experiment. Okay? That's just, that way I know that it's all still there, and I can then, once I have my spectra or my chromatograms or whatever it is that I'm running to characterize this thing, then I know once it's good that I can now get rid of everything. Okay, so if you get to that point on the first night, that would be awesome. Okay, so that's what the ether is. So now we're using the ether right in here to make sure that we pull this stuff out. Okay, and those are called, when we use ether, that's called a wash. We wash the water layer to get all the organic into the organic layer. Okay, shake, vent, shake the invent, and do that stuff. Okay, so now here in this we have ether, we have cyclohexanone, hopefully, and we have cyclohexanol. Probably just a little bit of this if we're really good chemists, okay? But now we have to make sure that we get rid of the ether. Okay, so the next night, what you're going to do is you're going to come back in, and you are going to dry the ether layer over anhydrous magnesium sulfate. Now, what does that do? Back here, let's go back here. Okay, so now we have our organic layer. Okay, and I'll keep it red. Okay. But there is a little bit of water kind of mixed in here. Just like little droplets that have made it around. Okay? We want to make sure that we remove all the water that we can. Water is the bane of every organic chemist's life. So, in order to get rid of all the water, we add an anhydrous salt. The anhydrous salt in this lab's case is, I believe, mag sulfate. Okay, magnesium sulfate. We call it mag sulfate. And we're going to add some of the mag sulfate. Now that's anhydrous. Ether won't absorb into here, but because water will absorb into here, any remaining water will absorb into the mag sulfate, and now our ether layer will be completely dry. That's what we call it. Dry, free from water. Okay? So, now, lost my train of thought here. Okay, so that's what the anhydrous magnesium sulfate is. But now, as we keep going through, we have an organic layer with a big clump of solid in here. Okay, well, in order to get rid of that solid, we have to filter it off. So what we're going to do is we're going to set up a kind of a standard filter procedure. Okay, we always filter into a flask. You know, it would be really good, actually, if you filtered into a round bottom flask. Then you don't have to transfer it as much. But you're going to fold filter paper, okay? And you're going to then wet the filter paper with a little bit of the solvent, ether, to seat it. That seats the filter paper onto the funnel. This is just a regular glass funnel. Make sure the funnel is glass, okay, not plastic, because if it's a plastic funnel, plastic can sometimes be dissolved by whatever solvent you're using. So you want to make sure you use a glass solvent, or a glass funnel. And then you're going to add this into there. So now what happens? The sodium sulfate is not green, or magnesium sulfate is not green, but that's what I'm using it for. The magnesium sulfate is going to be here, and all of the organic layer is going to be dripping in down into the round bottom flask. So now what this is this is going to be the this should be at this point no water. It should be primarily cyclohexanone and probably a little bit of cyclohexanol, hopefully just a little bit. Bleach is a pretty strong kind of household oxidizing agent, so it pretty much oxidizes the junk out of everything. So so at this point now, and there's also a whole bunch of ether in there. So now we want to purify and get just the cyclohexanone. So in this lab, what we're going to do is we're going to use the rotovaps, okay? Instead of doing this, okay? For this lab, we're not going to do another distillation. What we're going to do is we're going to do a rotary evaporation using the rotovaps in the lab. What that is going to do is get rid of the ether, so now the ether isn't going to be there, and now you're just going to have these, but you're primarily going to have this left, okay? And so you're going to rotovap it, and then that's going to be kind of the end of the procedural lab. The purification of this compound takes 4 times as long as the actual reaction. You know, the reaction's going to take a half an hour, 40 minutes. The purifying, the workup, the steam distillation, that itself is going to take 2 hours, and then you're going to have to do all the workup. So it's kind of a pain in the neck. Okay? So once you get done with that, you're going to let it dry. You're going to put it in your drawer. Hopefully that's the end of the next night. And then the last thing you're going to do is then the following week, you're going to let it sit in your drawer for a week so that we're sure all the ether evaporates. You're going to do a refractive index. Okay, you're going to measure the refractive index, and you're going to, in your lab report, compare the refractive index to the experimental refractive index to the literature refractive index. You're going to do an IR, which is super straightforward. You are not going to do NMR, nor are you going to do boiling point. We may or may not do gas chromatography to see how pure it is. That's interesting, but sometimes the GC, I don't know, it's finicky sometimes. But we do have a new GC on it. So anyways, so that's the pre-lab for this reaction. Those are all the reasons behind all the steps that we're doing. To summarize some of the safety concerns, okay, just bleach, kind of the normal safety concerns. It will dye clothing. Right, we all know what bleach is. Glacial acetic acid is strong, and if you touch it, consider yourself burnt, so we need to make sure we do that. Cyclohexanol is an organic compound and can be an irritant. It smells kind of bad, so just be careful of that. There's no overwhelming safety concerns with it, but just, as always, be careful. And then cyclohexanone, again, is pretty good, but to handle, it's very similar to cyclohexanol. So keep in mind that you're going to get a liquid here. Okay, so when you're calculating yield, because I want to make sure that I talk about this, and I understand this is 30 minutes into the video, but remember, you do this now, we don't have to do it in class. Okay, so one of the things that you want to make sure you do before you get to the refractive index and all what we call the characterization is you want to make sure you find the mass of the product. By finding the mass of the product, that allows you to calculate a percent yield. So just make sure that you get that done. So feel free to take this video, rewind, fast forward, anywhere that you need to in order to find out questions or to have questions answered. If you have any questions about the content, make sure that you write them down, because one of the first questions that I'm going to ask is, are there any questions about the Prelab? I probably will, because I'm a safety nut. I probably will review the kind of the safety procedures just one more time, and then we will get started. So that is the Prelab video for Lab 9, the oxidation of cyclohexanol to cyclohexanone.